Okay, so the first primitive regarding the Shor's algorithm we are going to discuss will be the quantum Fourier transform. For those of us who have engineering background, we are all familiar with the Fourier transform, discrete Fourier transform, or fast Fourier transform, various versions of Fourier transform. They are very common in signal processing communication systems. If you want to represent a signal in a frequency domain, right? In another basis, basically in a frequency domain, you would use Fourier transform algorithms. So quantum Fourier transform is also very similar. But let's see how we implement quantum Fourier transform using quantum circuits. Quantum Fourier transform can be visualized as a change of basis from the computational basis, which was Cat0, Cat1, to Fourier basis. So you can one can visualize this, in this shown in these graphs. Let's assume these are our block spheres, right? Block sphere representation of the Cat0 vector was this. And the Cat1 vector was this, right? So if you apply a quantum Fourier transform to a single qubit, right? What it does is it basically transforms this state, computational basis state, Cat0 or Cat1, to what we call a Fourier basis state. Right. In the case of single qubit, Hadamard transform corresponds to, as we are going to see shortly, to a quantum Fourier transform. And as we know, what this Hadamard transform does is it transfers the Cat0 vector to a Cat plus vector, which I'll denote as Cat0 tilde. Tilde indicating we are talking about now the quantum state in the Fourier domain, right? And similarly, when you apply quantum Fourier transform, in other words, when you apply with operate with the Hadamard transform on the Cat1 state, you would obtain the Cat minus state. So all quantum Fourier transform does, it's basically a change of basis. You start with a quantum state in the computational basis, and as a result of the quantum Fourier transform, you obtain another state on the equatorial plane of the block sphere. So this is what we call quantum Fourier transform. It is the exact same notion of Fourier transform that we have seen in the classical context, but in the quantum context, as far as the block sphere representation is concerned, it is just a change of basis from the computational basis to the Fourier basis. Okay. So more formally, let's see what we mean by quantum Fourier transform and what kind of a circuit that we can build using the single qubit and double qubit quantum gates that we could be able to implement quantum Fourier transform. So we first start with the formulation of quantum Fourier transform, and then we build the related circuit, accordingly. So let's suppose again we start with an n-qubit system with 2 to the n basis states, right? This corresponds to all combinations of zeros and ones of n bits, right? There are 2 to the n such basis states. And the quantum Fourier transform, which I will denote as Cat x tilde, quantum Fourier transform applied on Cat x, in computational basis is just like all the other operations we use in quantum computation. It's a unitary operation. I mean, it has to be a unitary operation. And we define the quantum Fourier transform applied on the state ket x as 1 over 2 to the n over 2. This is again we are talking about a quantum state. So this is the normalization of the state vector. And we sum over all y equals 0 to the 2 to the n minus 1. So sum over all combinations of ket y multiplied by this phase, this weighting factor as phase, right? This is a phase because it is in the form of e to the I theta, an angle e to the I theta. And this phase for each y is, and for the given input ket x, is computed and summed, over for each ket y. So this is, by definition, what we mean by quantum Fourier transform. It's basically the same definition as the classical discrete Fourier transform. So you have, let's say, a signal in the time domain in the classical case, and through this kind of a transform, an operation, you convert it in the classical case to the frequency domain. So this is a similar situation, and we denote this factor over here, e to the I 2 pi over n, right, as w, for shorthand, and this is also at the same time defined as the nth root of unity. Why is it nth root of unity? Because if we consider e to the I 2 pi equals 1, right? So this is 1. And if you divide this phase by capital N, you are basically computing the nth root of this. This is unity, and you are computing the nth root of unity. So in the case for small n equals 1, in other words, we have a single qubit, and capital N now equals 2 to the n equals 2. We have the case that we have seen over and over again. This equation, this transform, corresponds to ket 0 tilde, right? Tilde again, because we are talking about the transform domain, right? According to our notation we introduce here. Ket 0 tilde now becomes, if you plug in, the numbers ket y, because now we are summing over two states. Ket y now it's either ket 0 or ket 1. And if your input is again, if your ket x is ket 0, right? If you sum these two terms, you end up with 1 over square root of 2 ket 0 plus ket 1, which was our ket plus state. So as we had shown on Bloch sphere, at the beginning of this lecture, using this quantum Fourier transform expression, the ket 0 state is transferred to the ket 1 ket plus state. Similarly, if you apply this quantum Fourier transform operation to the ket 1 state, right, you would obtain 1 over square root of 2 ket 0 minus ket 1, which was ket minus state. So Fourier transform, this expression transforms, as we discussed, for the case of single qubits, it acts like the Hadamard transform. It transforms the ket 0 state to ket plus state, which is the state on the equatorial plane. And it transforms the ket 1 state to the ket minus state. So this is the case when we have a single qubit transform. But in general, if you have n qubits for multiple qubits. This quantum Fourier transform expression, this expression over here, can be expanded as follows. So this is again 1 over 2 to the n over 2, just the normalization factor. Cat 0 plus e to the I 2 pi x over 2 to the first power cat 1. I'm just now writing out, this expression for quantum Fourier transform. I'm expanding this for all because I'm summing over cat y, right? All combinations of cat y. Now I'm expanding this, assuming I have in the input a state, quantum state cat x. So this is cat 0 plus e to the I 2 pi x over 2 to the first power cat 1, tensored with cat 0 plus e to the I 2 pi x over 2 to the second power, tensored up to the nth qubit, cat 0 plus e to the I 2 pi x over 2 to the n cat 1. So if you expand this out, this is what you get. So this is how we define the quantum Fourier transform of a state cat x in the computational state, which we denote as cat x1, x2 up to cat up to x sub n. By applying this quantum Fourier transform, unitary transformation, you obtain cat x tilde in the transform domain as cat x1 tilde x2 tilde dot x sub n tilde. So we note that all of these actually components, that we tensor product, right? They are on the equatorial plane. So each one of these x1, x2, x sub n in the computational basis, they are either cat 0 or cat 1. All of them, they are transformed to quantum states in the equatorial plane with a phase angle of e to the 2 pi x over 2 to the j, right? So in the most general case, right, we could represent quantum Fourier transform as applied to one of the qubits of this series of this quantum state, input state, as cat x sub j. Let's say one of these qubits has state cat x sub j. Again, x sub j is in it's either 0 or a 1. It's in the computational basis. We obtain another qubit in the transform domain that is on the equatorial plane, right? This is 1 over square root of 2 cat 0 plus e to the I 2 pi x over 2 to the j. J is the index, index of this qubit, cat 1. So term by term, right? So in the input, in the computational basis, we have cat x1 tensored, cat x2 tensored, cat xn, and in the output, we have again tensor product of n terms, like n qubits, but at this time in the equatorial plane with these phases, with these phase angles. Another additional note. X over here in decimal notation, right? So if you have a string of bits x1, x2, x sub n in decimal notation, you would be able to denote this as 2 to the n x sub 1. These are x sub 1, x sub 2, x sub n. It's in binary form. So if you want to convert a binary string to a decimal number, right? This is 2 to the n x sub 1 plus 2 to the n minus 1 x sub 2 plus plus the final last term 2 to the 0 x sub n, right? This is how you convert from binary to decimal. If you have a bit string, of n digits, like this, n bits, like this. Just to illustrate this further, let's take an example for n equals 3. Now, for small n equals 3, that means we have 3 qubits, and correspondingly, we have capital N equals 8, 2 to the 3, 8 possible quantum states. So we'd like to find the quantum Fourier transform of Cat5. Let's say in the input we have the Cat 101 state, and in the decimal notation, this corresponds to 5, because 101 in binary is 5, in decimal notation. So we want to compute the quantum Fourier transform of this state, Cat 101. This is 2 to the 2 plus 2 to the 0, right? This equals 5. So 101, this is how I convert 101 to 5. And if you compute quantum Fourier transform of Cat5, first of all, this normalization is 1 over square root of capital N. Now my N is 8, so 1 over square root of 8. And then term by term, I transform, each one of the qubits. I have Cat 0 plus e to the I 2 pi 5 over 2 to the 1, Cat 1. Tensor product, Cat 0 plus e to the I 2 pi 5 over 2 to the second power, Cat 1. And then finally, I have tensor product, Cat 0 plus e to the I 2 pi 5, which is my input, over 2 to the 3, Cat 1, right? So each one of the terms in the input, x1, x2, x3, they are transformed through the quantum Fourier transform to these terms. Okay, so this is how we can express or define quantum Fourier transform. So in summary, I think it's important to note this, or the outcome, of this quantum Fourier transform lesson would be: you start with in the input Cat X, a quantum state in the computational basis, which is Cat X1 tensored with Cat X2, tensored with up to Cat X sub n. Again, all these Cat X sub I, they are in the computational state, so that means they are either Cat 0 or Cat 1. This is the input of the quantum Fourier transform. And in the output, you just compute the tildes, of each one of these. So Cat X tilde is Cat 1, Cat X1 tilde, tensored Cat X2 tilde, tensored up to Cat X sub n tilde, right? This is your output. And since quantum Fourier transform is unitary, right? So by just so QFT dagger, right, should equal identity, because it's by definition it's a unitary transform. If you apply QFT dagger, right, to this quantum state in the transform domain, you would obtain back the quantum state in the computational basis, right? So just to illustrate once more, each qubit X sub j, right, on the block sphere, right, this is my computational state, let's say, of X sub j on the block sphere, it is transformed to another quantum state on the equatorial plane with a phase, right? You have on the equatorial plane, how do you represent a quantum state? You have Cat 0 plus Cat 1 with a phase in the front, right? So this is, if the phase would be 0, you would be just at this location, Cat plus state. But then by adding phases, right, you are basically rotating around this equatorial plane. So according to this quantum Fourier transform, for each X sub j, this qubit would attain an additional phase of e to the I 2 pi x over 2 to the j, in front of the ket1. So this has a phase of 2 pi x over 2 to the j. This is the phase, of this. Okay. So this is the summary. I think it's important, to remember this. So now, how can we represent this formal expression of quantum Fourier transform in terms of a circuit, in terms of a QFT circuit? So the quantum Fourier transform circuit, it uses two components. One, the Hadamard transform, and Hadamard transform itself is actually can be represented as we have seen as a single qubit quantum Fourier transform. So one is the Hadamard transform, let's say applied on a quantum state x sub k, would transform this state to, in the transform domain, a quantum state ket0 plus e to the I pi x sub k ket1, right? Because if x sub k is 0, x sub k is in standard, is in the computational basis, so it can be 0 or 1. So when x sub k equals 0, this would correspond to ket0 plus ket1 state, which is the plus state. On the other hand, when x sub k equals 1, right, this phase would be minus 1. E to the I pi minus 1 is minus 1. So this state would correspond to a ket minus state. So we can represent the Hadamard transform, conveniently, like as this expression. And the second component that this QFT circuit uses is U0 sub k. Yeah, so it's a unitary rotation on the state x sub j with a parameter k. K would determine basically the phase angle, or that's the in the binary string, right? That's the location of the qubit. So it determines the phase angle that would be applied. So this is the second single qubit operation that we'll use in quantum Fourier transform. So it can be represented in operator form, in a matrix form like this, right? I mean, if you apply the zero state, which is the column vector of 1, 0, right? Ket0 would be the column vector of 1, 0. You would end up with 1, 0 again. So this U0 sub k transforms ket0 to ket0, right? It doesn't do anything on it. It doesn't apply any phase or anything. But if you apply this operator on ket1, which is column vector of 0, 1, right? If you apply to this, so it picks up this phase, e to the 2 pi I over 2 to the k, right? So this is what U0 does. If x sub j is 0, it does nothing. It doesn't add any phase. But if x sub j is ket1, it adds, this phase in front. Okay. And we also note that this tensor product form, right? We have shown over here the general Fourier transform, right? Each one of the qubits in the transform domain is transformed like this. But then if you multiply this out, if you compute this tensor product, right, you would end up with terms like phase terms that is related to the position of the one state in the input, right? For instance, a term like this, if you have 1 in the n minus first location, right, it would bring in a term like e to the I 2 pi over 2 to the n minus 1 phase, in front of the quantum state. So for each one, right, in the input, in the computational basis in the input, when you compute the tensor product, multiply out, in the front of the quantum state, you would have phase contribution. Like in the case when you have all the qubits equal 1 in the input, right? For each one, you would have a phase like this, right? For the first one, for instance, you would have e to the I 2 pi x over 2 to the 1. And then for the second one, you would have a phase e to the I 2 pi x over 2 square. And then up to the last one, e to the I 2 pi x over 2 to the n. So each one, ket1 state, in the input, it introduces a phase, like this. But the zeros, they don't introduce a phase. Because over here, right, this tensor product of quantum Fourier transform, if you multiply this out, for the zeros, you don't have any phases in front of the zeros. But for the ket1 terms, there's always a phase factor. So this is where we get these phase factors from. Okay. So this can directly translate it to a quantum circuit as follows. So this circuit, we claim, computes the quantum Fourier transform of an input state ket x and obtains ket x tilde. And these are x1, x2, x3, x sub n. These are my input quantum states. What this circuit does is it first applies an Hadamard and then controlled URAT2. Remember, 2. This was sub k was the location of the digit of the binary bit, right? URAT2 and then URAT3 of this was the location of this was the third bit in the binary string up to the nth bit URAT sub n. I'm applying a controlled operation because I want to apply this URAT only when this corresponding qubit equals 1. I'm just trying to imitate, this basically this equation. I'm just imitate this expression over here in terms of this circuit. So to x1, I applied Hadamard first, and then I applied URAT2 only when x sub 2 equals 1, right? And I apply URAT3 only when x sub 3 equals 1. If x sub 3 equals 0, I do nothing, right? This is how we operate controlled unitary operations, right? If the control bit is 0, we do nothing. If the control bit is 1, then we apply the unitary transform. This is how we have been defining, controlled unitary operations. So up to the x sub n. So let's analyze this more formally. Yeah, I mean, it is not difficult, to see that this circuit actually now represents this quantum Fourier transform expression. But let's see it a little more formally, step-by-step analysis. So in step 0, we start with the quantum state x sub 1, x sub 2, x sub n. This is my input state in the computational basis. So x sub I now is a 0 or a 1. And this string of binary bits, I would like to compute the Fourier transform. So step 1, now I apply this Hadamard transform, right? To the first qubit. If I apply the Hadamard transform, I have ket 0 plus e to the I 2 pi over 2 to the x1, right? I mean, if x1 is 0, right? This exponent is 0, so I have the plus state, just like we have seen, a few minutes ago. And if x1 is 1, then this exponent becomes -1, so I have the minus state. And all the remaining x2 dot x sub n, they remain the same, because I'm applying this Hadamard transform to the first qubit, right? All the remaining qubits, they don't get affected. And then in step 2, I apply the CRAT, the controlled unitary rotation, and this is this part of the circuit. Now I have applied the Hadamard. Now to the first qubit, I'm applying controlled URAT2. Controlled URAT2 applies this phase only when x2 equals 1, right? When x2 equals 0, it doesn't do anything, because again, that's how we define a controlled unitary operation. And all the remaining qubits, they remain the same, x2 up to x sub n. So up to the nth step, where we apply the controlled URAT sub n, right? So this URAT sub n, so this is applied to the first qubit only when x sub n equals 1. When x sub n equals 0, right, we don't do anything. So this applies in the nth step, an additional phase e to the I 2 pi x sub n over 2 to the n. And if you add up, all these phases, right? This is since the phases are in the exponent, right? We add up these phases. We end up with exponential of 2 to the pi I, and then we have this expression, x sub n over 2 to the n plus x sub n minus 1 to the n minus 1 up to x sub 1 to the 2 to the 1. But this sums up to n. Remember the definition of x in decimal form. So this corresponds to exponential of e to the I 2 pi x over 2 to the n. Because of these x sub n are in binary form, and then when we convert this from binary to decimal, we obtain this expression. So after n steps, as we have seen, when we apply this Hadamard and then URAT 1, URAT 2, URAT up to URAT n to the first qubit, we obtain cat 0 plus e to the I 2 pi x over 2 to the n cat 1. Tensored x2, x3, and x7, all the remaining qubits, they remain the same. But then we do the same thing, right? We do the same thing for the x2, x3, and up to x7, same operation to the other qubits. Now this time we apply the Hadamard to x2, and then we applied URAT 3 and up to URAT n. And then similarly, we operate the same on x sub 3. We first, it's not shown over here in this circuit, but when you extend this to n qubits, you apply first Hadamard and then URAT operations, similarly up to nth qubit. So this is the circuit for quantum Fourier transform and the analysis.